Okay, so yeah, on this video here, what we're gonna do is cover the rest of the learning objectives. Okay, and let's start off with the very first learning objective. So for alternating currents also, they want you to be able to understand the different terms here, which are like period, frequency, peak value, root mean square value, to alternating current or alternating voltage graph. Okay, and this one's actually really easy. If your foundation is good on waves, they basically are the same things. Okay, but I still have a page on this, so I can just give you a quick overview on this. Okay, so you can head over to page 1, it's all actually there. Right, so yeah, the period here, right, refers to the time taken for one complete cycle. Then the frequency, right, is the number of complete cycles per unit of time, or in 1 second. Okay, and then the peak value, this one's important. Peak value, right, is just the amplitude. So basically you can think of it as the maximum magnitude of current or voltage. Okay, and then the mean value, on the other hand, is not the same as root mean square. The mean is just the average value. Okay, and finally, root mean square value, right? This is the most important one that you must remember. So it was the definition that we went through already. Okay, and so looking at the graph, yeah, we can very quickly run through how it is illustrated. Okay, so the logic is, if they ever ask you for the peak value, they're asking for this guy, the maximum value. Yeah, and then the period you can find here. And then to find the frequency, right, you just have 1 over t. Okay, and it's quite important you also remember from oscillations and waves how you can describe this function mathematically. Right, and so the idea is just follow this. Right, it's the same exact setup as oscillations. So if it's a current graph, it's I naught sine omega t. If it's a sine graph, right? If it's a cosine graph, then yeah, I think you get the idea. It will be cosine omega t. Okay, and so yeah, actually this is a couple of learning objectives that we've killed off already. It's a really short chapter. Okay, so yeah, I'll cancel off learning objective A, and I also can cancel off learning objective C. Right? So we have done this, we've understood all the important terms. We've also known how to represent an AC mathematically using this. Okay, and so yeah, we also covered in the last video the key formula that you'll keep using, which is I RMS equals to I naught over square root 2. And then VRMS is also the same thing, V naught over square root 2. Yeah, and we know the difference now between the root mean square value versus the peak value. The peak value is just the amplitude, whereas the RMS value, right, you have to calculate it out using this if it's alternating current following a sinusoidal graph. Yeah, that's it. Okay, so yeah, we are pretty much done with these 3 learning objectives. Now, so the next thing, right, that is more important now is actually how to prove learning objective B. Okay, if you look over at learning objective B, they're wanting you to understand, right, that the mean power for a sinusoidal alternating current is actually just half of the peak power. Okay, and this one I can prove to you quite easily. I recommend, right, you follow me as I draw and explain it out. Then that way you can really get it. Okay, so I'm going to create a new page and take a look at this. So suppose, right, I have this setup here. It's an alternating current like this. Okay, and I have a light bulb like that. Then the idea is, let's say, right, the graph looks something like this. Okay. Let's say the current graph looks something like this. Okay, I should make it a sinusoidal graph. So let me just shift it a little and draw something like this. Okay. Let's say this is a perfect sine graph. Okay, ignore my poor drawing here. Yeah, imagine this is a perfect drawing of a sine graph. Right, then this is I naught. And then this is 1 period t. Okay, so here, what is the expression, right, for the current going through the light bulb? I hope you agree with me, it's just a classic sine graph. So you can say the following: I equals to I naught sine omega t. Okay, and what if I want to go and find, right, the expression for the power through the light bulb over time? I hope you agree with me that this is actually going to be, we can use a couple of formulas. Okay, so we can use this. Power is current times voltage, or power is current square times resistance, or voltage square times, over resistance. Yeah. And let's say the resistance of the light bulb is R. Okay, then how do I actually get the power through the light bulb? Well, I hope you agree, right? The most convenient one to use is going to be this. Because actually I already have given you the current expression. Right, and you can easily go and find the power expression over time, easily with respect to time. Okay, and so how do we do this? Simple, because power is just I square R. right? So I hope you agree this is going to be a I naught sine omega t square times your constant resistance. So the resistance is R, so we just put it there, right? And so we get this I naught square sine square omega t times R. And I'm going to make it very, very like user-friendly, or rather easy to read lah, right? And I hope you agree I can write it this way. I naught square R sine square omega t. Okay? So we can actually draw out this power graph. And the idea is for your power graph, right, it will now be a sine square graph. So the whole value is going to be positive all the time. So we can label that the power with respect to time graph looks something like this. Right? And then like this. And mind you, this is 1 period. Okay, so yeah, that's how you can think of it. Okay, wait, let me prove to you why. So I can actually draw a dotted line down with respect to the current graph, something like that. Right, then look, if you square the current graph, right, this part becomes, the bottom part here actually flips around and becomes positive. Okay, so the power time graph, right, will look something like this. Right, and like this. Okay, and then this value is the peak power, which is I naught square R, which is also the same thing as saying, oh, that's my maximum power, P naught sine square omega t. Okay, so we can call this P naught, which is the peak power, and this is T over 2, and this is T. Okay, yeah, so this is how you can get the power expression with time. So power is just P naught sine square omega t. Okay, and important thing to take note of is, once again, this is a sine square graph. So if it's a sine square graph, how do we find the mean power? Let's try to find the mean power, P. Now I hope you agree with me, right? It's just going to be the area under the graph for 1 period over 1 period. Yeah, so that is actually how you can get the mean of anything. So the mean of any value, right, you just find the area under the graph for 1 period, divide by 1 period. Yeah. Okay, so here, how do I get the mean? I just go and find the area under the graph here, right? Like that. Then I divide by 1 period. And don't panic, okay, because this is a sine square graph. So you must remember this trick. For all sine square graphs, right, this area is actually equivalent to the area of the rectangle that is halfway cut through, something like this. Okay, and once again, I've shown you this before. The logic is basically you can cut and paste this fella here. You can cut and paste this fella here. Okay, and so that's why, right, once you shift this down, you cut and paste this block here and here. Then the area, right, of the yellow part, right, the area under the graph of the yellow part, is actually also going to be the same as the area of the rectangle. Okay, that looks like this. Okay, so actually the area under the graph is really quite easy. So look, this was P naught, right? Which is I naught square R. I hope you agree that if I cut it halfway, then this is just P naught over 2. Okay, so the area under the graph, right, is actually just P naught over 2, right, which is the height here, times the length. And the length is 1 period. So P naught over 2 times T over T. Okay, and then check it out, it's P naught over 2, because the T's will cancel. Okay, so if you're given a normal alternating current graph, right, then you can find the average power, right, P, as just the peak power over 2. Okay, so yeah, this is another learning objective you gotta remember. Okay, and good news is here lah. Right, so that's written here. Mean power in a resistive load is half the maximum peak power for a sinusoidal alternating current. So we're done with learning objective B. Okay, and now the next one. So they also want you to remember, right, for a simple iron core transformer, that you can use this equation. Okay, and this one I've actually covered under electromagnetic induction. So if you are not too sure about how this works, head over and watch the EMI recording. Okay, so I'll kill off learning objective E. Okay, and finally, look at the last part. So this one is very commonly tested out. So sometimes they also want you to understand how the single diode, right, can be used to rectify an alternating current. So let me explain to you what I mean by this. So rectification, right, is actually just the process of converting an AC current into a DC current. Basically what this means is we want to ensure that current flows only in one direction. Okay, so I'll give you a quick example. So suppose we had an alternating current that looks like this. What this means, right, is that for half the period, right, the current will come out from here and then go around like that. And then for the next half of a period, it will go the other way around. Right? So what if I have certain devices that I actually only want current to flow in one direction? So imagine I only want current to flow this way. Right? Then actually what you can do, right, is just use a diode. Okay? So a diode here restricts the current flow to one single direction. Okay, and let's draw a diode now. So the diode can look something like this. Right? And this diode here, right, just means current can only flow in this single direction. Okay, so suppose, right, that my original graph before I put the diode was like this. Okay, let's draw the following answer. IT. Then my current would look like that, right, originally. Okay, now what will happen, right, once I put the diode in? Then the idea is, for the half of the period where the current tried to flow in the other direction, actually the diode will prevent current flow. So it will kill off this part. Okay, and so yeah, then with this, right, your new current time graph, right, just looks like that only. Okay, and so over time, right, the cycle will repeat like that, and then all the negative parts, right, all gone. Yeah. So basically, the diode only restricts the current to the positive parts of the graph. There are no more negative values really. That's how a diode works. Okay, and important, so they love to test this in the exams, right? So how do you get the IRMS? Let's write the following. So what is the root mean square value of a alternating current with a diode? Can I still use this equation? Can I still use IRMS equals to I naught over square root 2? Can I use this? Then the answer is no. Okay, this only works if it was a normal alternating current that was sinusoidal. Right, meaning it only works if your full sine graph is there or your full cosine graph is there. Okay, so this one no go already, it won't work already. Okay, and so actually if they give you a diode and then they ask you to find the RMS value, how do you get it? Simple. Just use the same 3 steps. You first need to square, then mean, then root the graph. And then you can easily get the IRMS value. Okay, and so I know the answer already is going to be IRMS. For the ones with a diode, it's just going to be I naught over 2. Okay, and I'm going to prove this to you, and I really recommend, right, you do the same thing with me. Okay, so we'll start on a blank page, and let's consider this. Okay, and so I'll write the following. Finding IRMS for graph, for sinusoidal current with a diode inside. Yeah, so let's draw the following. So real quick, this is how it looks like. You have a current time graph like this. IT. Okay, and I'm going to draw 2 periods just so you can visualize what's going on. So this is going to be half a period. And then for the next half a period, right, look, it's going to be flat. It's going to be 0. So I'll draw a little meter like this. And then this is 1 full period. Okay, and then the process will repeat itself. So basically it'll look like this. Okay. Okay, yeah. Okay, and so yeah, this is how this will look like over multiple periods. Okay, then this is 2t, and then this is 1.5t. Okay, all the negative parts, right, that used to be here, right, all gone. They're now 0. Okay, so that's what I'm showing if there was a diode. Okay, and to help you visualize this, I'll draw the following. Okay, so current only can flow in the positive bias direction, forward bias direction. Basically, current only flows when it's going in the same direction as the diode's arrow. Right, yeah, so current can't flow in the other half of a period. Okay, so this is the IT graph. Okay, and current in amperes, time in seconds. Now, how does the RMS values work? Right, so look, step 1. Before you do anything else, right, just square the graph. Okay, so we need to go and find the square, then the mean, then the root. Okay, so the very first thing to draw is the I square graph. Let's draw this. Okay, and you know what? I should follow the graph on top lah. Okay. Now I'm only going to draw positive values because the moment you square anything, all values become positive. Okay, so this is going to be I square slash A square and T slash seconds. Okay, and just now, right, this was a I naught. Right, so once you square the graph, right, I hope you agree, it becomes a very nice shape like this. Oh, and let me be clear. Let me draw this. I will show the marking out like that. Okay. Very nice. Okay, yeah. So now, how does the I square graph look like? Well, it's like your sine square graph. Okay, and so you get something like this. And then 0 here. Alright, so 0 here. Okay, and then after that it repeats itself like this. And then 0 again. Yeah, so this is a squared graph already. Okay, and so this is t over 2. Okay, and then this was I naught square. Okay, so step 1 done already, right? We square the graph. Now what is step 2? Find the mean square current. Basically, after step 1 of squaring, right, the next thing is find the mean. That's it. Okay, so finding the mean is easy. Remember, right, the mean square current basically means the mean of the square current. Right, so we've already squared the current graph. So the mean is just area under 1 period divided by 1 period. Okay, and so here's the fancy thing. This is still a sine square graph. So it's very easy to find the mean. Right, I hope you agree with me. I just need to consider this aspect only. I need to consider the first period here. Okay, if you're wondering how come I don't need to consider the second period, right? The answer is just the whole function, right, is periodic, meaning it keeps repeating itself. So actually you only need to care about one period because all the following periods, right, it will be exactly the same process. It will repeat itself. Okay, so that's why you only restrict your analysis, right, to one period. Okay, and so basically find the area under the graph for that first period. And it's quite easy. So look, if I want to find the area of this this whole part, let's shade it in blue. What do I do? So we've learned the technique just now, right? If it's a sine square graph, I can just cut this into 2. So this will be I naught squared over 2. Right? And then I plug this part, put it here. Then plug this part, put it here. Okay, and the idea is, well, the area under the graph for the first half of a period will just be the area of this box. Very nice. Okay, and so then what is the area of that box? It's just going to be I naught squared over 2 times t over 2. Right, so that's the area under the graph of this part. Right, so the green is equal to the yellow, which is here. Okay, yeah, so then from there I found the area under that section already. Okay, next, what's the area under the next half of a period? What's the area under here? But the answer is 0, right? Because there's no current there at all. Okay, so I can just plus 0. Okay, so the next half of period, right, nothing really. Then I just divide by 1 full period. Okay, so yeah, so let's simplify this. You get I naught squared over 4 times t over t. And check it out, the t's will cancel again. And so you end up with I naught squared over 4. And this is the mean square current. Okay, so step 2 is done. Congrats. The last step is the easiest. Step 3. Find the root of the mean square current. Okay, so this is it. Find the root of the mean square current. IRMS is just the square root of this. Right? And you got this already, right, just now? So it's just square root of I naught squared over 4. And ta-da, you get I naught over 2. Okay, so yeah, I hope this is easy. IRMS is I naught over 2 if there's a diode in a sinusoidal current or sinusoidal voltage. Yeah, so this is very, very common. Okay, so this is actually the last learning objective I have. Here, we can strike off the following. Explain the use of a single diode for half-wave rectification. Done. Okay, now here, look. We have learned how to apply RMS calculations also for when diodes are present. So done with this. Okay, and in the earlier video, right, I also show what if they give you other shapes of alternating currents. For example, when the current is not constant and is a rectangle, right, like this. Like that, and like that, and then like that. Right, then how do you find the root mean square value? Easy. Just follow the same steps. You square the graph, you mean it, and you find the square root of it. And then you're done. Okay, and so one last tip for you guys for this chapter. And this one, if you've seen me teach this in class, I always say the same thing lah. Okay, so look, I'll draw it out for you real quick. If you are ever doing the squaring of a sine graph, so let's draw this. Once again, this is current with respect to time. Okay, so let's say this is like that, right? And this is I naught sine omega t. Now, some people, right, when they are too hasty with the drawing, let's say they want to go and draw the I square graph already. Okay, they might actually think that it's like that, but it's wrong. Okay, so look carefully. So a common mistake is this: they think that the positive part stays like that once you square it, and then the negative part, right, just flip upside down. So people have this impression that it's like that. Okay, this is wrong. So look, there's a very, very simple thing that your teachers are always checking for. They want to make sure that once you square the graph, you know that it's not going to be sharp here. It shouldn't be sharp there. Right, so there's actually a way that we remember this. So this is wrong, this is no go. Okay, so look, this is called McDonald graph. So we say no McDonald. Okay, what do I mean by no McDonald here? I'm trying to tell you, if you want to draw a sine square function, right, it shouldn't look like a McDonald graph. You know the McDonald symbol? Yeah, it shouldn't look like that. Instead, the correct answer, right, is a smooth curve that looks like this. Okay, and so take note, it must be a smooth curve like that. Okay, so note there was no sharp edges. The original one that I drew just now that was wrong was sharp like that, right? So sharp like that and then up. This one is wrong. Okay, so the correct one is the blue one, which I've just sketched. Okay, so there's this simple phrase, and I really hope you remember, which is no McDonald. Okay, and also remember, for all your sine square graphs, this here was one period, right? So your sine square graph will also have that same feature. One period, right, is these two peaks, right? Then it's one period. Okay, yeah, if not, I think this chapter is honestly very short and very easy. And whenever it comes out in the A levels, right, you are expected to get full marks. Don't screw this up. Okay, this video is only enough to get you through the concept and the bare minimum understanding of the calculations. To get very good at this, I highly recommend you do a lot of practice questions. They're the freest marks to earn in the exams. Okay, and if you want, you can head over to the website. Right, so there are plenty of practice questions for you to try here. Just quickly do them. Okay, yeah, no, I hope this was helpful. Yeah, cheers.